Rugged. The product should be tough. It shouldn't break too easily or too soon. The parts should be made out of strong materials. In every class of material, there are tough options. Among metals, there's mild steel. There are millions of truck chassis and locomotive frames and excavator booms with cracks in them out there. And mostly, these keep working just fine for a long time because mild steel resists the growth of cracks. With plastics, a lot of modern power tools are made out of glass-filled nylon. And you could take one of these tools and throw it on a concrete floor, and the material will resist the impact. It won't be permanently damaged. And glass-filled nylon is more impact resistant than its predecessor, die-cast aluminium. With wood, there's lignum vitae. This is so wear resistant that it can be used for the soles of woodworking planes and the stern tube bearings of ocean-going ships. The parts should also use strong shapes. When a part transmits a force from one location to another, the part is strongest when it transmits the force along a direct path. If this path becomes roundabout, circuitous, it creates bending moments in the material, and these create high localized stresses, and then you have to use more material to compensate for having this indirect path. If you think of a handsaw, doesn't matter if it's a bow saw or a hacksaw, this has a C-shaped frame which tensions a straight blade, and the blade carries the force along a straight path. It's very thin, but the frame, which has to carry the force indirectly around the circuitous path, must be much thicker and more sturdy because the path is indirect. Also, when a force changes direction in a component, then it's important that this change of direction is gradual, that the component has smooth curves, and maybe if it changes in thickness, that this also happens gradually. It's like if you have a rope and the rope is in tension, then if you want to make it go around a corner, you've got to push sideways on the rope. And if you want it to go around a corner suddenly, that force is very concentrated. It's the same in the material. When the direction of the stress changes, then you end up with transverse stresses at 90 degrees, which push or pull it around the corner. And the more abrupt the transition, the higher these transverse stresses. This is why a crane hook always has a smooth curve, has no sharp corners, because these would create very high stresses and break the material. And if you think of classically strong shapes, like a stone arch bridge, this is strong because it carries the compression along a straight line through the stone without bending it. And a triangle is strong because it doesn't bend any of its joints. Which brings me to the next point. Your product should have well-considered joints. I can't say to you that it should have as many joints as possible, or as few joints, or the strongest joints, or the stiffest joints, because the topic is complex. Adding joints creates modularity, so it's easier to swap broken parts. But extra joints can introduce weaknesses and additional manufacturing costs, and sometimes they come undone unintentionally. And also, it's not always what you want to have a really stiff joint, because a more flexible joint can absorb impacts and it can direct forces to other stronger components. It's like if you have a jackhammer, then the handles are very rarely attached rigidly. Either they're on pivots or they're on rubber blocks, so that the force from the hammering action is isolated from your hands. Your product should also tolerate wear and abuse. If you make a rear hub for a bicycle, which can offer different speeds, you shouldn't find that after it's been ridden for a few thousand kilometers, then it won't go into gear, or it jumps out of gear. Or if you make an office stapler, then you shouldn't find after stapling a few hundred sheets that it starts to jam. So it's very important to test your mechanisms with high tolerances, with worn components, to make sure that they survive and stay reliable. And it's not always the case that simple mechanics are the best solution. A carburetor in a petrol engine is quite a simple mechanism, but it's delicately balanced. It's prone to wear, and it's sensitive to misadjustment, and fuel injection and electronic engine control, although they're more complex, are actually more reliable. And people are also likely to abuse things. You know, if it looks like a handle, it'll get used as a handle. If it looks like a step, it'll get used as a step. So you need to think like the abusive product owner to create a tough product. Lastly, your product should age gracefully. That means when it develops signs of age, chipped paint, scratches, knocks, cracks, that it should look appealing. These should be signs of character. A metal like brass, for example, develops a beautiful patina over time. A wood like mahogany, if it gets some knocks and irregularities, cracks, it still looks beautiful. And you should be thinking about these things at the time of design and think, well, how is my product going to look in 10, 20, 30, 50 years' time? And there are small design changes that you can make as well, using a minimum of surface coatings, because the surface coatings then cannot wear off. And having rounded corners, because rounded corners don't lose their paint so easily, and they don't damage other things that they knock against. So it's important to pick materials that age gracefully, in contrast to things that don't, like, for example, fiberglass or melamine. Most composites, they don't age well at all. My example for rugged is this. It's a drilling hammer made by Estwing of the United States. It's descended from hammers that were used literally to drill holes in the era before electric or pneumatic drills. So you take a special chisel and hit it with the hammer, and every time you hit it, you rotate it a little, and it removes a few chips of rock. And gradually, over the course of hours, the miner would be able to drill a hole. I'm now going to compare the Estwing one-piece drilling hammer to 5 other hammers, some of which have been repaired by other people in the past. The idea of making a hammer as 2 parts, a head and a handle, doesn't really bring any advantages. It's more of a carryover from the past, when it wasn't possible to make the head and handle as a single piece because of the materials or manufacturing processes. And the tradition was to use a wooden handle like this, which was then wedged into an eye in the steel hammerhead. And the problem is that this tends to fret a bit. And you can put a steel wedge in here, and you can drive it in and hit it now and then to make it tighter. Or you can design a handle that has a taper in the handle itself and pulls itself deeper inside the head, but it never completely gets rid of this fretting. And you also see quite a lot of wear on the soft material here when people maybe don't hit that accurately. And with this hammer, you can see that the owner has added a nail in the end of the handle to try and expand it and make the head fit tightly. And when that hasn't worked, 2 screws. And then a plastic wall plug. And still, the head is loose on the handle. And if the owner of the hammer is more inclined to metalworking, you sometimes end up with a repair like this, where the owner has put a steel tube inside the eye here and welded it on, a bit messily. And here, the owner's also added a couple of angle brackets for reinforcement. And it's quite an ugly repair, but it works, and it keeps the hammer in service. Here's a much neater repair. This is quite an unusual hammer. I think it's intended for panel beating. It's made by Hardwick of Sheffield in England. And you can see that when the wooden handle has broken, the owners added a thick-walled tube, put it through the eye, and then cut 4 notches, and then bent these 4 sections of the wall out to wedge it in the eye. And it's been tack welded and completely welded around the back here. And this is a brilliant repair. This hammer will never need fixing again. And Estwing's idea is to forge both the head and the handle as a single piece. And they've chosen the alloy steel well. It's been hardened and tempered correctly, so it's nice and strong, but it's not too brittle. These heads, they don't wear much, but they also don't develop cracks. And the bevel around the edge of the face helps with that. You can also see the curve to reduce the stress where the handle joins the head. But with a steel handle, it would be a bit uncomfortable to hold without a grip. It's not as comfortable as a wooden handle, especially since the handle here is quite thin, like the shaft of a spanner. And so what Estwing have done is to add a one-piece molded rubber grip. And they've done this very well, because there's a trend among tool manufacturers to use a so-called 2-component grip, like this. This is actually a good example. It's done quite well. The red here is hard plastic, and the black is soft rubber. And this is something that's difficult to get right. You have to have the correct material combination and the correct temperatures in the process, things like that. Otherwise, this black rubber is very prone to peel out of the recesses. And that leaves a sharp handle. It's worse than not having any rubber at all. Lastly, I've got a very old Estwing one-piece ball peen hammer. This, I should think, is 30 plus years old, and it's seen a lot of use. You can see it's quite worn, quite discolored, and yet it has an attractive patina, and it's still perfectly serviceable as a tool. You can use this hammer for anything. Ironworking, rigging, demolishing, even breaking rocks. I love it because it's so rugged it'll last you a lifetime and it won't give you a bit of bother.